So attenuation is not just a thermodynamic nuisance, as was the case with Pablo, but attenuation and isotropy can give you important physical information about subsurface rocks. Today we are not going to discuss all of this, but we are going to discuss one aspect of wave propagation in attenuative media. So that is modeling. So before I talk about all these modeling methods, it has been observed in rock physics experiments and in seismic data processing that the quality factor remains constant in the seismic frequency bandwidth. So this is not to be confused with alpha, but we are talking about Q. So this means that higher frequencies suffer more attenuation than lower frequencies. But this quality factor is constant in the frequency range of interest. So let's see how these modeling methods approach this problem, or how they simulate this physical phenomenon or observed phenomenon. So the reflectivity method can easily handle this. It can easily model attenuative media, anisotropy, etc. But it is limited for layer cake models, and so that means models with flat interfaces, and these flat interfaces also need to be symmetric planes, like orthorhombic media, for example. And finite differences also in the frequency domain can model this Q behavior very accurately, but you need a lot of computational resources to propagate waves in the frequency domain, different frequencies. In time domain, however, things get interesting. Because of this constant Q, you need fractional calculus. So which means that you apply tricks like introducing relaxation functions. And okay, you might model using these relaxation functions, but in the inverse problem, you're not inverting for Q, you're inverting for these relaxation functions. So for me, this is a very convoluted idea, and it's not really physically intuitive. Ray methods, however, can model the phenomena of constant Q. So you're not assuming any attenuation mechanism, but you can model this dissipation represented by constant Q. And they're also easier to implement as opposed to finite difference in time domain. So this is why I choose, as they're efficient and fairly accurate in not very complex media. And so we are going to talk about how we can use Ray methods to model attenuation. So to generate reflections, we use the familiar Kirchhoff modeling. And we'll be working in 2 dimensions, but all the stuff here is 2.5D. So the math on the top shows these the Kirchhoff Gaussian formula. What you need is some sort of a weighting function with all sorts of corrections for 2.5D. And you need these Green's functions from the source to the diffractor and from the receiver to the diffractor. And you convolve these Green's functions and sum over all the scattering points in the reflector. And this formula is equally applicable to attenuative media as it is for elastic media. Let's take a look at some Green's functions in attenuative media. So we have the Ray-theoretic Green's function here between any 2 points x1 and x2. So x2 is the source location, x1 is an observation point. And it involves several quantities. Among them are the elastic displacement, u0, the travel time, and the attenuation coefficient. The elastic displacement would include polarization vectors, geometrical spreading, reflection transmission coefficients, etc. And I've called it elastic displacement because of the way I compute this Ray-theoretic Green's function. So we compute u0 and travel time in a reference elastic media. That means given a model that is attenuated, we remove the attenuation terms, have this reference elastic media, and we do ray tracing in this media and compute u0 and the travel time. And the attenuation coefficient is is computed using ray perturbation theory, which was what I presented last year. And if you notice, there was the harmonic component in the Green's function, and then there was the exponentially decaying dissipative component due to attenuation. And to emphasize again, I'm computing this dissipation factor, which I've called T star from ray perturbation theory. So if you remember, we need 2-point Green's functions for Kirchhoff modeling. That means we need Green's functions for rays connecting the source to the diffractor point and those connecting the receiver to the diffractor point. But in ray tracing, as you're all familiar, there are some problems when you try to compute 2-point Green's functions. So the most basic problem, or the most simple problem is, so I've indicated this ray coming from the source, and maybe the best I can do is hit this point x. I might not hit xd. However, I can use an interpolation to compute the Green's function for the ray that connects xs and xd, etc. But 2-point, like ray tracing also suffers from multipathing, so amplitudes can blow up, etc. So we need something that can give us smooth amplitudes, because we are really interested in amplitudes here. We're dealing with attenuation in reasonably complicated media. And one such method is the method of summation of Gaussian beams. And that is what we will use to compute all these Green's functions. So just a brief review of what it is. So Gaussian beam summation. So you shoot a fan of rays from source location, or you spray a fan of rays, and then you put a Gaussian envelope on all of these rays and Gaussian spreads, etc. And you accumulate the contribution of all these Gaussians from these fan of rays at a point of interest. So here my point of interest is the diffractor location xd. So this is the math for what was happening in the last slide. You're interested in the Green's function from xd generated at xs in the frequency domain. It involves a certain weighting function and all these beams which were on top of these rays. So this is for elastic media. In viscoelastic media, things don't change much. The weighting function that was in the last slide remains the same, but instead of this elastic beam, we have this so-called dissipated or attenuated beam. And the attenuated beam simply has an extra term multiplying the elastic beam, which is e to the power minus omega t star, which is the dissipation. So let's take a simple example to see what this elastic beam and viscoelastic beam look like. This is a GB impulse for purely elastic medium. It's a monochromatic impulse response for 10 hertz. And I introduce a Q of, say, 20. And this is how the beam changes. So remember that this is a monochromatic beam, so we're not losing frequencies, but we're simply losing amplitude. So flip back and forth. And the dissipation factor which made this beam dissipative was computed from ray perturbation theory. So I want to show you some numerical examples of how the scheme performs. So the most simple numerical example for this would be reflection from a plane boundary. So we can verify how the scheme performed by comparing it against a reflectivity method, which computes exact seismograms for this kind of models. So here we show just 2 layers, 1 layer and a half space, in fact. The velocity and anisotropy parameters are on the left side. The attenuation parameters are on the right side. So QP naught is the familiar quality factor, except that it's what you get if you measure in the vertical direction. And QS naught is the same thing for S waves. Epsilon q and delta q are parameters which characterize attenuation anisotropy, and they describe the quality factor function as functions of angles, and they carry similar formulas as for the velocity anisotropy. And so before we compute reflections from this model, we would like to see how in the media above how the 2-point Green's functions compare. So remember that we compute these Green's functions between, say, the diffractor location and the source location using this method of summation of Gaussian beams, and these beams were attenuated. And for this simple model, I know where the rays are going. There's no multipathing, so I can easily compare the Green's function obtained from GB summation with those obtained from perturbation ray theory. And that's the comparison I'm going to show you now. So this is for a propagation angle of theta equals to 0 degrees. This is the impulse response. And the red is UGB, so that means what we computed from summing those beams. And URT is the impulse response computed from perturbation ray theory. And we see that there's quite a good match between the two. This is for 30 degree, 60 degree, and so on. So now we'll see how this reflected data compare. I'd like to remind you that we are basically using the Kirchhoff modeling formula, and we are plugging in the Green's function that you obtained from Gaussian beam summation into this formula. So that is what all the math shows here in this slide. So we'll now compare the seismograms generated by reflectivity method with those computed from this scheme. So this is the seismogram computed from the reflectivity method, and I've only computed the P wave displacement response, and I'm showing you the Z component. The source was also a vertical Z component source, and you can see at the farther offsets there's these wiggles are getting spread more and more, so that is attenuation. This is from reflectivity, and this is what we get from the scheme we proposed today. So Kirchhoff modeling formula, reflectivity, and Kirchhoff. To compare better, I'm taking traces at different offsets and see what happened here. So in the red is what we get from Kirchhoff, and the black line is reflectivity. There's a slight difference in amplitude, and but actually we're not interested in the absolute amplitudes when we look for attenuation. What we're interested in the shape of the spectrum. So this is the shape of the amplitude spectrum in the Fourier domain. So amplitude versus frequency. So you can see those nice exponential decay after a certain frequency, which is due to attenuation again. And we can see that the amplitude spectra match quite well, which means that we're in good shape. So this is for 0 offset. I'm going to show you the comparison for different offsets. So this is for another offset. So again, we don't care about the absolute amplitudes, but the shapes of the wiggles. And this is for the last offset. So next I'm going to show you an example with a layered VTI model. So this has 2 layers. The first layer is at a depth of 2 kilometers and it's flat. And the second layer is this anticline-like structure with its midpoint at 3.5 kilometers. The velocity in both the layers is increasing with depth. So this plot shows you the vertical P wave velocity and the anisotropy parameters, velocity and anisotropy parameters for each layer is shown on the right. And so there's only, I'm not showing you epsilon and delta fields, this is because epsilon and delta in each layer is constant. So this is the going back to the factorized models that characterize anisotropy, which means that epsilon and delta remain constant, but the p wave velocity increases. And using the same concept as for velocity, I'm going to show you a similar plot for the quality factor. So the quality factor is increasing with depth, and the attenuation and anisotropy parameters are shown on the right. And for this model, I'm in trouble because I can't use reflectivity method. Because remember that reflectivity method is valid for layer cake models. So what I'm going to show you is just the Kirchhoff scheme, and we're going to see what happened in this model with the wave propagation. So this is what the displacements we get from this scheme, and we can see that in the second event the wiggles died out sooner than in the first event, and this is because for farther offsets in the second event there's more attenuation, the ray paths are longer. This is I've just windowed the first and the second event. So this is event 1, this is event 2. Event 1 and event 2. So event 1, when I zoom out, there's still some energy in farther offsets, but in event 2, they die out quicker than in event 1. So to summarize this talk, we implemented Kirchhoff modeling approach for attenuative TI media, and the Green's functions inside this Kirchhoff integral were computed from GB summation, and these beams were dissipated beams, and this dissipation was computed from ray perturbation theory, and we compared a few examples for how this scheme is working for ray theory and reflectivity method. Thank you. I'd like to acknowledge first. I want to acknowledge Dave, Ivan, and John for answering my questions, and they're a wonderful resource. And also A-Team and CWP colleagues for good discussions. Thank you.